In this video, we're going to simulate the top half of our fountain using the basic flip sop tools. So carrying on from where we left off, we've got our fountain emitter here, which is our sphere with the noise and the velocities on there. And we have our source of the water, our water source, the geometry that's going to be the bed of the water. So we're going to set up, first of all, we're going to set up a rudimentary flip sim using these, the flip sop tools. So the first thing we need actually is to, like with all flip simulations, we need to define the container that the fluid happens in. And that's sort of the largest area that it can fill out the voxels. To do that, we actually, if we hit tab and type flip, you'll see we've got flip container, or you type flip container. So this will define where the bounds of the flip sim are. So if you turn this on and zoom out a little, or dolly out a little, you'll see that this blue outline. So this is the extent of the simulation. So any of the water that goes outside of here will just disappear. That's the gist of it. So traditionally this is squared. You can adjust that here. If you look at the settings, we've got the domain. So here we can adjust the size of that, and it's interactive as well. If you hit enter, you can do it manually like this as well. You can resize it, which is quite handy. What's really nice about this is you can actually plug some geometry into the top. So unlike the normal DOP simulation where you have this rather large box, which can make things quite inefficient if you want really localized stuff, is you can use any kind of geometry to create these bounds. It doesn't have to be square. For example, if I just take a sphere and I just plug the sphere in, you'll see, and I'll just make that larger, you'll see this is now the bounds of the simulation. So any water that leaves here will just disappear out the scene, which is really handy. And we can use that to our advantage, actually. We can make this sort of, instead of resizing this manually, because basically if I just display the fountain, I only really need simulation to be local to this fountain. I don't need any of this extra stuff out here. I mean, it doesn't really slow it down if you have it out there, but it's just when you sort of frame things, it just frames the whole box really. You want to sort of frame on the geometry. So what I want to do is just make this a bit smaller. So I'm going to use a bounds node. So we've seen the bound node before. This creates a bounding box based on a piece of geometry, a box based on the bounding box of your input geometry. So if I plug the fountain in and I display this or template the bounds, you'll see it creates a little box. Let me display the actual let me go back to shaded mode. So here I'm displaying the fountain and I'm templating the bounds. You'll see it's drawn a box to fit the bounding box of my fountain. So this is a great starting point of defining the bounds of where your sim goes if you make the bounds around all the geometry you're going to use. And then you can, the nice thing about this bounds node is that you can actually tweak it here. You can make some adjustments. So we can adjust the lower padding, upper padding in the X, Y, and Z. So the lower and the upper padding are often the negative and positive X directions. So if I just orientate this correctly, so that this way is positive Z, there you go, there's the little gnome on there. So now I can see which bounds I need to increase. I definitely want to increase the upper bounds. So for the upper bounds, let's put in, let's just increase that, well, that's this one here. Let's put 0.5 in. That gives us plenty of clearance up here. And then these other bounds I can kind of pretty much leave at the defaults if we want. If I get some fluid coming over the edge here, that'll just disappear rather than falling down the side. So we could maybe just expand those at 0.1 we want. Just expand those bounds a little bit. So any fluid that comes out might run over. Anything that splashes out will just disappear, but we'll be fine with that for now. But you could make this bigger if you wanted to. So that's sort of driven by our geometry, which is good. So if I now plug that into the flip container, you'll see, let's just template the fountain. You'll see the flip container fits nicely around there. And again, we can adjust this if we want to, make it a bit bigger and smaller. The other nice thing about this flip container is we've got some other settings here. First of all, we've got the particle separation. This is like a resolution of our simulation. This is how far apart each of the particles are. So it's in Houdini's scene unit. So this is basically every 10 centimeters we're going to get a particle. If we middle click, we'll see here, you'll notice that actually the voxel size is 0.2. That's because this number is multiplied by this. Okay, we're actually, even though we've got the particles separated by this amount, the actual volumes we're creating to solve the simulation are 2 times this. In other words, they're half the resolution. That's why you see it here as 0.2 instead of 0.4. So if I put this to 1, you'll see it's 0.1 now. Or if I put it to 4, you'll see it be 0.4 now. So the grid scale is reducing the res. This is, a quarter. This is a lot lower resolution than the flip. So ideally you want this at 2. Sometimes you want to bring this down to maybe 1.5 or 1, but that will make the simulation go slower. But we'll leave that there for now. You'll notice this is grayed out because we're using the input geometry. We can adjust gravity. Here we can adjust the density of the liquid. We can add surface tension. In fact, I'm going to turn on surface tension. We're not greatly on big scales. You won't notice the effect of surface tension, but this is quite small-ish and not that fast-moving, so we probably would notice some effects of surface tension. But I like to turn it on. We can also add viscosity if we want to, which I'm not going to in this example. And the other important thing is these attributes here. So here we can add various attributes, and we're going to need some of these later on for when we do the white water. Things like vorticity, relative density, and age. And it's a good idea to also have ID. That means you can delete particular particles if you want. Now I've got my look, I've got these going across here. There's a couple of things we can do about these bands. This is what I'm talking about, the connection here. If I'm coming down here, I've got this connection going across the network, which I don't really like very much. There's a couple of things we can do about that. The first thing we can do is hold down Alt, left click and drag in one of these, and we can make a dot. And the dot allows us to reposition sort of these connections nicely. The nice thing about the dots is if you delete, you can connect them to other nodes. So if you click up here, you can see the little down dot there. You can drag that out and sort of plug it in to another node. Or if you grab the top one, you can plug another node into the dot, which is quite handy. And you can make as many dots as you want. You can select them and delete them. You can even give them colors if you really want to. Let's make that white again, which is interesting. Or you can delete them. The other thing you can do is do Shift and S, and that will make the these noodles, these connections, sort of bend around, which is kind of a nice thing as well. I like to do that sometimes. So as a Shift S or with an Alt left click, you can make those dots. Anyway, we digress slightly. So we've defined a container for where the simulation's going to go. Don't forget to save if you're saving. So the next thing I want to do is define where our water is going to come from, or where the water is. And to do that, we use a flip boundary node. So let's make a flip boundary node. Now you'll notice there's 3 outputs coming out of these. If I just bring a null in for a sec just to see what's there, this first output is basically the volumes and anything else, any particles and stuff. So that's your fluid. As always, that on the left-hand side is the data Houdini deals with. So this is the important bit, the stuff on the left. This will be your particles and volumes. This middle one, if we have a look, this is just defining the container with these detail attributes. So it's just saying what the container is. You get a shape and you get various attributes that tell it things like the separation and grid scale and stuff. Out of this last one comes any collision objects. We don't have any collision objects plugged in, so we won't see anything out of there at the minute. And you can plug those into these 3 as we go. There we go. Let's turn this on. Now you won't see anything yet because we haven't plugged anything in. This last input is the geometry to source, and you'll see the type here says source. We can either source or sink. The sink is where we remove particles, but a source is where we source them in or we birth them. So I'm going to use this fountain source, this little sphere here. Let's plug that. Oh, missed the wrong input. Let's plug that in. Now if we turn this on, we should see something, but we don't. The reason we don't see something is because the lack of the resolution. If we go back to the container, remember I said this was, each particle is 10 centimeters apart. If we middle click on our fountain geometry, we can see our sphere is 0.04, which is 4 centimeters, not 10 centimeters. This is like half you're basically getting two of these entire things per particle distance in your voxel. So this thing here, what I'm trying to say is, this thing across its x-axis is 4 centimeters, whereas we're asking for one particle every 10 centimeters. So this is much smaller than the resolution of our flip sim. So we need to fix that really. So if I display the boundary here, let me template. Well, no, let's not template that. Let's just display the boundary. If I select the flip container here, let's drop the resolution down. Let's put 0.05. So that's still not enough. Remember, this is actually 0.04. So instead of 0.05, let's put 0.01. And there we start to see our thing being resolved there. And we can see it's moving, it's animating through time. So we'll probably need a higher res than this. Let's put 0.005. There we go. So we're talking, instead of 10 centimeters, 1 centimeter, this is like 5 millimeters now between our particles. We get a better resolution there, and you'll see the volume actually is double that. It's 0.01, so this is like 1 centimeter resolution. So now we can fix that. We'll probably want to go lower for the simulation, but we'll leave that there for now. So you'll notice on the boundary as well, it's going to, you can compute the velocity from the deformation, which is what we did on the point velocity here. This is calculating here where it says basic. This is calculating the velocity based on the deformation for us already. We're going to add some noise and some up velocity in a moment, but let's see how this looks. So, and we can add additional velocity here to the incoming velocity, so we can scale it up and down as well as calculating it, which is really nice. So the next thing I want to do actually is create another flip boundary, and this time source the body of water. So let's just plug these guys in. Let's grab that over to the water source. Let's turn this on. And if we come down, you'll see we have our water source down at the bottom there. So this is the extent of our simulation. Now, what I'm going to do also is add a flip collide. So this will tell it what to collide with, and you'll see it's much simpler, this workflow. You know, you create the boundaries where you want stuff to come in, you create the container for the initial, and then you create your collide node, and then that's pretty much it. So we kind of need node-wise for this setup. So this last thing is the collider, and this is going to be our fountain up here. In fact, let me just use this null, and let's call this collider. Let's just make that red. Let's select that, make that red. Let's plug this fountain in, and then I can take the collider here and just plug that in there. Just keeps the network a bit simpler. Let's do something like this. There we go. So as soon as we do that, you'll see it displays our geometry as a collider there. And you'll see it's creating a volume collider and a surface collider for us. And generally you can, if it's animated, you might want to increase the subsets, but generally you can leave these settings the same. For now, actually, I'm just going to disable the collider because I want to do some tests. And sometimes calculating the collisions can make it a bit slower. So just for speed of the test, I'm turning that off, but I know it works at the minute. So the next thing I want to do is just actually then create the flip solver. So the flip solver here, let's turn this all on, then takes all this data that we've created. In fact, let's turn the collider back on for the minute. Takes it all, and then this is what solves it frame by frame, hence the name solver. So this is the important thing here. And you'll notice things like the resolution is grayed out because it's bringing the information from the container, this blue input. So, but you can turn this on and override it if you want to, but generally I just drive it from up here because then I can preview what the boundaries are doing. So we'll go through some of these settings in a minute once we have it all set up. So this does take a while to do. The other bit we want to do actually, oh yeah, before we go anywhere, by the way, you'll notice that it's displaying the particles as these spheres. I find this can be quite slow to display, so I like to go to the visualization and just turn that off. And now I'm displaying them as points. I tend to find this is a bit quicker. So the last few bits I want to do is now add a flip compress node. Sorry, a fluid compress node. So let's type fluid compress. I can't type fluid compress. There we go. And let's plug this in. So the data you get out of a fluid sim, out of a flip sim, can be very intensive. Let me just disable and re-enable that. Can be very heavy because we've got lots of volumes at particularly high resolution. We've got lots of particle data as well with lots of attributes. And this can be quite heavy on disk as well as your RAM and everything else. So we use a fluid compress node to basically compress everything up. And this is kind of cool. What it does, it packs all your points into pack primitives and it saves them as these little boxes. So that's what these pack geo is. There's 295 boxes. Each of those have got a bunch of particles within them. And it's also, that's this pack particles. If I turn that off, you'll see we get the particles back and not the little boxes. We don't get the pack primitives. And then also we're reducing the data in the volumes from 32-bit to 16-bit, which doesn't change any of the fidelity of the sim, but it just means we save a lot less data on disk. And it's trimming out some of these volumes as well. For example, things like the pressure. Now you'll see it got rid of the pressure, but it's compressed down. It's converted all the Houdini volumes, the dense volumes into VDB sparse volumes, which again saves a lot of data on disk. So this is very efficient at trimming down what you need to save. So then we can add a file cache. And remember, we only need to save this left output here because this is where all the data is. This will be our volumes and our pack geometry. This is just a reference to the container, and this is just a reference to the collisions. So you don't need to write these out. But I am going to give this a name. I'm going to call this Fountain Sim. Yeah, that's it. So file cache Fountain Sim. The reason I'm doing that is because in the name here, it's using these variables to fill out the name of the cache. So $hip is where you've saved your scene to, the path. The hip name is the name of your scene, and the $os is the name of this node. So that's why I've given it that name there. You could put your own name here and then not use these variables, but I like to do it this way because then I can see what this cache is writing out to disk. And then we want to visualize this, but not as these boxes. So for that, I use a fluid surface node. You can plug your data into the first one, and again, your container as a reference there, and your collisions into the third input. When you turn this on, this is going to display it as a surface. So we don't display it as a surface at the moment. Let's turn it back to particles, and then we can visualize them with velocity, so it looks the same as the raw output from the flip sim here. But the difference is this is being cached, so we can save it to disk and then preview what's going on a bit later. So I'm going to go back to the fluid solver for a minute, and I just wanted to show you one other thing I want to set up. I'm going to go to the flip collide and just disable that for a minute, and then let's just press play. Because when we press play now, what we'll see is our little sphere here is emitting, which is all very good, but then you'll notice this body of water is constantly emitting as well. Let me just stop that. That's not something we want to be happening. So how do we fix that? Well, in this flip boundary here, this is the one, if I turn it on and off, is creating this body of water. You'll notice we've got this activation at the top. That means it's on. If I turn this to 0, it's off. So we can type an expression here. We can say $FF, so that's the floating frame, and then we can say if it's equal to 1. So when we put the two equals, we're saying, is this equal to 1? So at the moment on frame 1, it is equal to 1. So this resolves to a true, which is a 1. If I click on the word here, we can see the result of the expression. So if you left click on the word, you always see the result of the expression that you've written. If you click again, you'll see the expression. So this is saying when the current frame is equal to 1, is that true, which gives us a 1. And then if I step forwards a frame to frame 2, this is no longer true because the frame is not equal to 1. If I click on here, that's a 0. So if I keep pressing play now, you'll see it only emitted on one frame, on frame 1, and now it's just dropping through space, which is the effect we want. And you can see what happens if I just template the bounds. When it leaves the bounds, it just disappears out the sim. That's saving us calculating more voxels and stuff. Cool. So that's and then we can preview that through this fluid surface as well. You'll see it's just as quick to play back. So yeah, that's it for the basic setup. What I'm going to do now is tweak it and adjust the velocities on the top bit of the fountain here. So let's now adjust the velocities on the fountain spout here. Now there's no point me simulating this whole massive thing at the moment. So what I can do actually is just make a copy of this bounds node. That's with my original one, and let's select this one. So let me just show the fountain and template this. I'm only interested in what's happening at the spout of the fountain. So here I'm going to bring up the lower padding. So now we're literally just seeing what happens at the top here. Maybe bring that down. Yeah, bring that down a little so we can. Because maybe later on I'll keep the collision in and we'll see what goes over the edge. But for the now, I just want to leave the top bit open and not calculate this bottom body of water. Even though I've got this turned on, you'll notice if I turn the solver on now, that's out of bounds, so it's not going to show that body of water. So we're just calculating now what happens here. And if I press play, you'll see it goes quite a bit quicker, which is good. We can now test how we're going to make this spurt upwards. So the first thing I'm going to do is I'm going to go to the point velocity here and give it some upward shift first. Let's maybe put this to 3 and see what that does. There we go. If we shoot that up to 3, that kind of comes up quite nicely. And what you'll see is we do have a bit of a stepping issue. Plus as well, it looks a bit too uniform. I want that to look a bit more watery and noisy and randomy. We've got the mountain here, which is helping. It's adding a bit of noise to that. If I turn the mountain off, you'll see that's even smoother. So look, it just looks like a cone. So if we turn the mountain on, now it looks less like a cone. It's a bit more broken up, which is a start. But I want to vary it by adding some more noise to the velocity here. So to do that, we're going to add some curl noise to this. So let's turn on the curl noise and see the effect of that. Well, that's interesting, but it's a little bit on the large side. So let's just bring down the swirl size here to something quite small. Remember, this thing here was only, what did we say? It was like 5 mil big. So if I make the swirl size of the noise about 5 mil, it's roughly the size of this thing here. Let's see that as a starting point. Oh, that looks kind of interesting. There you go, that's broken up a bit more, and it's given me that sort of irregular, zigzaggy top here that I was after. Well, that's looking actually quite nice. So if you want to see this play back in real time, you can click on this little clock icon here, and that guarantees it's never going to play faster than 24 FPS. But how do you know if what FPS it's playing? What you can do to find out the FPS is either click on this little eyeball down here, or tap D. So if you put your cursor over here and tap D, it'll bring up display options. We can go to guides and turn on draw FPS. There we go. If I press play now, you'll see we're playing back at 24 there. Obviously not. We're caching. Yeah, I'm liking sort of that. I'm going to make the noise animate actually. Let's take the pulse duration down to something like 0.2. So it's going to see what kind of noise we got now. We have now. It's quite aggressive. It's actually spraying the water out quite a bit. And if I just template my fountain, actually, it's going to be hitting the sides and splashing everywhere. So maybe that's a little bit aggressive. Let me just reduce this scale down. Let's try 0.2. So I don't want it that mad and crazy. I just want a bit of a nice natural break up to it. Kind of nice-ish. Maybe 0.25 or 0.3. Let's try 0.3. So that's kind of nice. Quite leisurely. I don't want it too noisy, but I just want a nice sense of breaking up that cone. A few spouts, because it's quite an even flow. There we go. To fix that stepping, really, we can go to the solver here. And if you go to the first tab, we can increase some of the substeps here. Let's go to 4. And you'll see that just gets that little bit smoother on the source there. And we see a much nicer sort of resolution or definition, yeah, resolving the noise a bit better. That's the better way to say it. It resolves the noise a bit better. Just gives you more fidelity. But for speed, we'll keep this on 2 for the moment, but I probably will end up adjusting that a bit later. So the other thing is, we'll notice as soon as we step forward, it's got this big shoot in there. What I'm going to do is I'm going to animate that on a little bit so it just comes on a bit more naturally. It's always a good idea to animate your noises on. So here I'm going to do this on the point velocity. Now I want to animate this and these scales, this velocity here and this scale. Actually, we don't need to do that here. What we could do is come to the flip boundary. We could animate the scale velocity here. If I set this to 0, you'll see there is no velocity. We set this to 1, have the full velocity in. So we'll just scale it up here, to be fair. I'm going to set this to 0 and just right click, go to keyframes, set keyframe. And you'll notice the shortcut's Alt left mouse button. There we go. Let's play forwards to about 1 second, about frame 24. Go forwards. Oh, that goes to the end. Don't want to do that. That's frame 24. Let's set this to 1. And then let's click on the little key down here, and that'll just add another keyframe for us. And we can tell by our green ticks. There we go. Let's go back to the beginning. So press play. It will gently spray in rather than just kicking in. This is always a nice thing to do with your simulations when you're sourcing, is just to fade them in. So it gives it a much more natural start than all these crazy velocities at the beginning. So that fades up and goes off. Cool. Let's turn on our collider and then see how water come on. You'll see it's a bit slower with the collider in there. But now it's hitting the collider and filling up in the base here. And you'll see we really don't have anything like the resolution that we need at the minute, because it's all quite sparse and quite separated particles. So what I'm going to have to do is I'm going to have to increase the resolution. So come down to this guy and see what's going on there. And once it's colliding, we've got this more interesting sort of sploshy behavior going on there. It's filling up this pan and starting to run off over the edge. So what I'm really doing now is I've got the geometry and I've run a system in and it appears to be working, but there's a few other things I want to add to it to make the water seem more sort of natural and things. And we do need to increase the resolution, which is going to slow us down. But you'll notice I'm trying to work efficiently and quickly, which is why I'm sort of using these limited bounds. So I'm going to go back to the bounds for a minute. Actually, I'm going to reduce this lower padding. I'm going to bring it down further. So we're allowing that to go a little bit further, but not quite splash in there yet. Let's come up a bit. And let's press play. See how far that's going to go, because I'm interested in how it runs over the edge here now. We've got a nice sort of fountain source going. And I've made it slightly bigger, which is going to slow me down slightly. And I want to see it running over the edge here. It might take some time to fill up, but I don't have that many particles. And what we'll see is, even though for me it's going fairly quickly, but for you guys, you might want to pause, go a bit longer. There we go. We can see it starting to run off the edge here. And it's cascading over, which is kind of nice. But let me just template the fountain for a minute. There we go. And we can see it's coming out and it's flying out over the edge there, which is a nice effect, a nice effect in itself. But this is quite small scale. And if you imagine when you see fountains like this, they're often wet under here as well. And anybody that's knows that when they try to pour a jug of water, or water out of a glass, sometimes the water comes out the glass like this, but other times it runs down that edge in a quite annoying fashion. So water tends to cling to things and run down the edge sometimes. It's attracted to stuff as it comes down. And it gives it a much nicer effect. The problem with the flip at the minute is there's like zero friction, and the water just glides along and then flies out like this, which on large scale water probably is what's happening, but on small scale water, it tends to stick to things and run down edges and things like that, and it's a really nice effect. And we can actually simulate that effect here in Houdini. If we select the flip solver and go to collisions, you'll notice we've got a stick on collision. So what I want to do is I want to mess with this and get a nice sort of sticky effect of this coming over the edge. So what we'll do is we'll stop the video now, and in the next video we'll look at how to create that sticky effect.